Hello everyone and welcome back. In our previous lecture, we have systematically explored linear data structure like array, linked list, stack, and queue, along with flexible key value stores like object, map, and sets. These are fantastic for organizing data in sequence or associating values. Today, we are taking a significant leap into the world of non-linear data structures, tree, heap, and graphs. These structures are designed to represent more complex relationships between data elements than simple sequences. They are fundamental to fields like artificial intelligence, network analysis, database indexing, and much more. Imagine your data set is not just a list, but rather has hierarchical relationships like a family tree or interconnected relationships like a social network. That's where tree, heaps, and graph comes in. We will focus on their core concept, their common variations, and their characteristics time complexities, rather than diving into the detail of their implementation. Let's explore these powerful ways to model complex data. Let's begin with the tree. In computer science, a tree is a non-linear data structure that simulates a hierarchical tree structure with a root value and subtree of children with a parent node, represented as a set of linked nodes. It's like an upside down natural tree. Here is a conceptual representation of the tree, where each element in the tree is called node. The topmost node of the tree that has no parent is called root. The link between two nodes represented edge. A node that has child nodes called parent. A node directly connected to another node when moving away from the root called child. A node that has no children called leaf. A node and all its descendants called subtree. The crucial rules for a tree is that there are no cycle. You cannot start a node, follow edges, and return to the same node without backtracking. There are many types of tree, but one of the most common and useful is a binary search tree. In a BST, for every node, all value in its left subtree are less than the node's value, and all value in its right subtree are greater than the node's value. This specific ordering makes searching very efficient. Let's discuss time complexity for a BST. Here, search insertion and deletion operation in average case is big O log n. This is because just like with binary search on a sorted array, you effectively cut the search space in half with each comparison. If you have n elements, it takes roughly log n steps. This is incredibly fast for large data set. And search insertion and deletion operation in worst case is big O n. This occurs if the tree becomes unbalanced and essentially degenerate into a linked list. For example, if you insert elements in strictly ascending or descending order. In this scenario, you might have to traverse all n nodes. Trees are fundamental for organizing hierarchical data, and BST are excellent for efficient searching, sorting, and maintaining ordered data. Next, we have the heap. A heap is a highly specialized kind of binary tree that satisfies the heap property. This property dictates a specific relationship between parent node and their children. There are two main types of the heaps. Max heap, where the value of any parent node is always greater than or equal to the values of its children. This means the largest element is always at the root. Another is mean heap, where the value of any parent node is always less than or equal to the value of its children. This means the smallest element is always at the root. Here is a conceptual representation for max heap and min heap. Crucially, a heap is typically a completed binary tree. This means all levels are fully filled except possibly the last level, which is filled from left to right. This completeness allows heaps to be very efficient, represented and manipulated using an array, where parent-child relationship can be calculated using simple arithmetic on array indices. Let's look at the heap operation and time complexity. Here, insertion or adding an element is big O log n operation. When a new element is added, it's initially placed at the end of the heap. To maintain the heap property, it's then bubbled up by swapping with its parents until its correct position is found. In the worst case, this involves moving from leaf to the root node, which is proportional to the height of the tree, log n. Another operation is deletion of root, getting the maximum or minimum element. This operation is also big O log n operation. To remove the root, which is always the max or min element, the last element in the heap is moved to the root's position. Then this element bubbles down by repeatedly swapping with the larger or smaller childs until the heap property is restored. Again, this is proportional to the height log n. Next operation is peak, getting the maximum, minimum element without removal. This operation is constant operation big O 1. The maximum or minimum element is always at the root, so accessing it is a constant time operation. Heaps are primarily used to implement priority queue, where elements are processed based on their priority, and for efficient sorting algorithms like heap sort. Finally, we arrive at the graph. A graph is most general of the non-linear data structure. It's essentially a collection of nodes, often called as vertices, and the connections between them, called edges. Think of a social network where people are nodes and friendship are edges, or a map where cities are nodes and roads are edges. Graph can model virtually any kind of network or relationship. In graph, the elements themselves called nodes. The links that connect two nodes called edges. If edges have a direction, for example, one-way street from A to B, if you can go from A to B, it doesn't necessarily means you can go from B to A. So this type of graph is called directed graph. If edges are bidirectional, for example, a two-way street between A and B, if you can go from A to B, you can also go from B to A. So this type of graph is called undirected graph. If edges have associated values or weights, for example, distance, cost, or time, that type of graph is called weighted graph. Unlike tree, graph can have cycles, meaning you can start at a node, follow edges, and return to the same node. Here is a conceptual representation of the graph. This is an undirected graph with 5 vertices, A, B, C, D, E, and 6 edges. Graphs are commonly represented in two ways: adjacency matrix, a two-dimensional array where matrix I, j is 1 or the weight if there is an edge from node I to node j and 0 otherwise. Second is adjacency list, an array where each index represents a node and the value at that index is a list or array of its neighbor's node. This is often more memory efficient for sparse graph. Graphs are incredibly versatile and are used to solve complex problems across many domains. Working with graph often involves running specialized algorithms to extract information or solve problems. Here are a few fundamental types: traversal, shortest path, spanning tree, topological sort. So let's discuss one by one. Traversal algorithm. Here idea is systematically visit every node and edge in the graph, essential for exploring a graph structure. We used following algorithms: breadth first search, BFS, which explores level by level, visiting all direct neighbors of a node before moving to their neighbors. The time complexity for this algorithm is big O B plus E for adjacency list and big O V square for adjacency matrix. Another algorithm is depth first search, DFS, which explores as far as possible along each branch before backtracking. The time complexity for this is also big O V plus E for adjacency list and V square for adjacency matrix. Next is shortest path algorithm. Here idea is find the path with the minimum total weight like cost, distance, time between two nodes or from a source node to all other nodes. We use the following algorithm, Discasta algorithm. It finds the shortest path from a single source node to all other nodes in a graph with non-negative edge weights. It works by greedily selecting the unvisited node with the smallest known distance. Time complexity for this is big O v plus e log v or big O e log v. Simpler array-based implementation are big O v square. Another algorithm is Bellman-Ford algorithm. It finds the shortest path from a single source node to all other nodes, similar to Discasta algorithm, but it can handle graph with negative edge weights. It works by repeatedly relaxing, updating all edges in the graph v-1 times. It can also detect if a negative cycles exist, which would mean no shortest path is defined. The time complexity for this algorithm is big O v e. Slower than Discasta for non-negative weights, but crucial for negative weights. Another algorithm is float-VARCHAR algorithm. It finds the shortest path between all pair of nodes in a graph. It works by considering all possible intermediate nodes between every pair of source and destination node. And the time complexity for this is big O VQ. This is suitable for graphs where you need to know the shortest path between any 2 points. Next is spanning tree algorithm. Here idea is for a connected undirected graph. A spanning tree is a subgraph that connects all the vertices together without any cycle and using the minimum possible number of edges. A minimum spanning tree MST finds the spanning tree with the smallest possible total edge weights. We use the following algorithms like Prim's or Kruskal. These algorithms are used to find an MST. Prim's algorithms grows a tree from a starting vertex, while Kruskal algorithms edit edges in the increasing order of weights. The time complexity for these algorithms typically big O e log v or big O e log e or big O v squared depending on the specific implementation and data structure used. Next is topological sort. Here idea is for a directed acyclic graph, a graph with directed edge and no cycle. Topological sort produces a linear ordering of its vertices such that for every directed edge u to v, vertex u come before b in the ordering. Think of task dependency. For example, task A must complete before task B. So the time complexity for this algorithm is big O v plus e. These algorithms forms the bedrock for solving a vast array of real-world problems. Let's ground these abstract concepts with some real-world application. For tree, file system. The way files and folders are organized on your computer, folders within folders, is a classic example of tree structure. The root is your main drive and subfolders are children. Similarly, XML, HTML, document structure DOM, the document object model in web browser, which represent the structure of an HTML or XML pages, is a tree. Elements are nodes and nested elements are children. Database indexes. Database used a specialized tree called B tree to efficiently index and retrieve data, allow for very fast searching on large data set. Decision tree in AI. In machine learning, decision trees are used for classification and regression, where each node represents a decision based on a feature. For heap, priority queue. Heaps are the most common way to implement a priority queue, where elements are always dequeued based on their priority. For example, task scheduler, where urgent tasks are handled first. Event schedulers. In operating systems or real-time applications, a heap can manage a list of events to be executed at a specific time. Always prioritize the next event. Network packet handling. Routers might use heaps to prioritize network packets based on urgency of type of service. For graph, social network, like Facebook, LinkedIn, Twitter. These are all massive graphs where people are nodes and friendships are edge. Graph algorithms are used for friend suggestion, feed ranking, etc. GPS navigation for shortest path. Google Maps and other navigation systems use graph algorithms like Discasta to find the shortest or fastest route between two locations, where cities or intersections are nodes and roads are weighted edge. Bellman-Ford can be used if routes can have negative cost. For example, free highways offsetting toll roads. Computer network, the internet itself is a massive graph, with computer or server as nodes and network cables or wireless connections as edges. Graph algorithms help route data packet efficiently. Recommendation system, service like Netflix or Amazon use graph to recommend movie or product based on what similar users like or what you have interacted with. Project management for topological sort. If you have a list of tasks where some tasks depend on another task, like build walls depends on lay foundation. Topological sort can give you a valid order in which to complete these tasks. Alright, let's quickly recap our journey through these advanced data structure and their powerful algorithms. We started with tree, understanding them as hierarchical structure, especially binary search tree, allow for efficient searching, insertion, and deletion typically in logarithmic time. Then we explored heaps, which are specialized tree for managing priority, ensuring quick access to the maximum or minimum element, with all core operation being highly efficient in logarithmic time. Finally, we covered graphs, the most general non-linear structure capable of modeling complex interconnections. We discussed common way to represent them and then covered crucial graph algorithms. For traversal algorithm like BFS and DFS, exploring graph and edges. Various shortest path algorithm like Discasta for single source and non-negative weights, Bellman-Ford for single source but capable of handling negative weights, and float VARCHAR for finding shortest path between all pair of nodes. Minimum spanning tree algorithms like Prims and Kruskal, which connect all vertices with the least total edge weights. And topological sort for ordering tasks in a directed acyclic graph based on their dependency. Each of these data structure and algorithms has a specific purpose and time complexity, making them suited for different types of problems. Understanding their basic concepts and when to apply them is a cornerstone of efficient problem solving in computer science. That's all for today. I encourage you to look for example of these structures in the software you use daily and think about how they might be working behind the scene. This deeper understanding will truly empower your programming journey. Thanks for watching.